of Greenland, that anthropogenic climate change is unequivocal and ongoing. So what is the problem with recent climate change trend then? It seems like natural causes is also changing climate all the time. So what is the problem right now? The plot is showing the Northern Hemisphere temperature over the last 1,000 years, and this is also a famous hockey stick plot by Michael Mann et al. And you can see that in the blue lines where temperature is recorded in tree rings, corals, ice cores, and other historical records has been pretty stable over the past 1,000 years. But in the recent or last centennial change recorded in red in thermometers, you can really see that the temperature rise has been too fast. And what does that mean then? So going future, we really need to project what path we're going to take and the consequences of that. So the here is showing the projections of global and regional temperature relative to 1995 and 2014. And depending on this, this blue arrow is supposed to be indicating that what we agreed on during the Paris Agreement, which is 1.5 degrees warming by the end of the century relative to the third industrial level. And we can really see that these different projections start diverging after around 2040. And so the decision that we make today really will matter tomorrow, which also then implies the importance of taking immediate action. And so this plot showed the global mean value of temperature rise, but when we go into spatial pattern of temperature rise across the globe, then things start looking more interesting and complex. So here is what the warming across the globe would look like, showing the annual mean temperature change by 2100. Panel A showing change at 1.5 degrees global warming, which we agreed on at the Paris Agreement, and B showing change at 2 degrees, and this bottom left panel showing change at 3 degrees global warming and 4 degrees global warming at the bottom right. And you can really see that the changes are pretty drastic, especially as we go beyond 1.5 global warming. Things start looking pretty red all over the world. And also you can see that these polar areas are going to experience even higher global rise, temperature rise relative to the global mean level suggested. And that is because of what is called polar amplification. And now to see the differences between the global temperature change between 2 degrees and 5 degrees, we can see that the difference is pretty significant, especially in the polar region already and in the continental regions. And in the middle section here, difference between 3.3 degrees versus 1.5 degrees, things are looking pretty red. And so that's about 1.5 degrees difference. And you can see that in the polar regions and this high up hemispheres, the difference is actually greater than 3 or even 4 or more than 4 degrees. Yeah, so the difference between 2 degrees and 1.5 degrees, which is 0.5 degrees again, and the polar regions, and on the continental regions, the difference is actually greater than 0.5. So this is really a good reminder for us to keep in mind that globally average difference of 0.5 degrees or 1.5 is not very small when it comes to regional differences. So here I'm showing the consequences of global warming in different levels, taken from the last ICCI report, and how the world could get actually warmer. It's showing the projected annual average temperature change relative to the pre-industrial levels at different levels of global warming again, and change at 1 degree global warming, which we've already achieved, looks like this, and change at 1.5 global warming, we are getting more intensified signals in the polar regions across the globe, And at the bottom left, it's 2 degrees change global warming, which is getting more intensified signal and saturated signals compared to 1.5 level. And when it comes to 4 degrees, then it gets really, really bad. So this is another reason why we would like, we need to take immediate action to limit global warming as much as we can. And this is showing the projected sea changes in the intensity and frequency of hot temperature extreme over land, and specifically showing frequency of intensity and frequency of 10-year events. So this means that at the pre-industrial period, this event would happen once in 10 years. But at the warming level of 1.5, it'll start happening around 4.1 times in 10 years, and 2 degrees, 5.6 times more, and 4 degrees warming level 9 times 4 times compared to the previous year level. So what it used to be a 10-year event now has becomes an annual event, which is pretty scary. And for the 50-year events, things also start increasing in terms of frequency and intensity. So we're just focused on 1.5 versus 2 and 4. So for the event that would happen once in every 50 year in 1.5 degrees warming world, it will happen about every 8 times of every 50 years, so that's almost 1 year over 10 years, or 1 time in 10 years. And in the 4 degrees warming, in the warm world, now it's going to happen about 39.2 times in 50 years. So that is pretty significant increase as well. So now when we talk about global warming, we can't put aside sea level change. So what has been happening in sea level as we've been warming the Earth? In the early 20th century, the sea level rise in global level used to be about 0.7 millimeters per year. And during the mid-21st century, it increased to 2 millimeters per year. And then lately, it's been increasing and accelerating, and now it's at about 3 millimeters per year. So the problem really now is that what is going to happen, and what is the sea level change going to look like in the future? So people started to project sea level change, or ice sheet contribution to sea level change, and these different colors reflect sea level changes projected to sea level projected to rise in different emission scenarios. And RCP 2.5, 2.6 is shown in the blue level, and RCP 4.5 is shown in purple. RCP 8.5 is shown in red in high emission scenario. And you can really see that the sea level rise starts accelerating in this very high emission scenario, and also the possibility of the range of possible sea level rise increases with the strength of emission. And that has to do with the uncertain, or it has to do with the future dynamics or behaviors of ice thickness. And we have ice sheets in polar regions, and in the Northern Hemisphere, we have Greenland Ice Sheet, which holds about, which is holding about 6 meters sea level equivalent ice volume. And in the Antarctic Ice Sheet, Antarctic region, the Antarctic Ice Sheet is holding about 58 meters of sea level equivalent ice volume. But just to give you a bulk comparison, 6 versus 16 is about 10 times larger. So yes, these are the 2 potential largest contributor to future sea level rise over centennial or decade timescales. And when we think of what's going to happen to sea level, how is it going to rise when we melt these polar ice? It is shown in this plot where we imagine sea level rise to be globally uniform, right, for the market backdrop. But that is actually not what happens in reality. And so what happens is that the sea level rise will be pretty complicated and complex in geographical pattern. So this plot is showing what would the sea level change rate when we melt the Greenland ice sheet to raise sea level about 1 millimeter per year. So 1 millimeters per year is going from, it's right there between black, blue, and yellow colors. And so when we melt Greenland, you can really see that this saturated gray regions are the regions where they're going to experience sea level fall. And the blue regions is where it's going to experience sea level rise smaller than the global mean value. And the orange and red regions are where global sea level rise is going to be larger than the global mean. And on the right hand side, the pattern gets flipped. The gradient of the color gets flipped, and this is when melts Western Antarctic Ice Sheet. So why does this pattern then appear? That is because there are some physical processes going on. So first of all, when ice sheets melt, the solid earth that has been compressed underneath the ice mass starts lifting, causing relative sea level fall. And at the same time, there is weakening of gravitational attraction from ice into the ocean. And ocean water or any sort of fluid rests on the gravitational and the potential surface. So when there's in the gravitational weakening case scenario, the water level starts migrating. So the combination of sea surface height drop and the solar earth uplift contributes to local sea level fall as reflected in the gray regions. And on top of that, there is what is called the rotational effect. So when polar ice sheets melt, the rotational axis moves towards missing mass, where the ice mass is being lost. So this shift in or perturbation in the rotational vector of the Earth will also cause this quadrant pattern for the globe. So these little bulges or the colors showing red and orange are the cause of the rotational effects. So all these three processes together are called gravitational, rotational, and deformational effects, and they're interrelated to each other. And so importance of this GRD effects is that it allows fingerprinting sea level change depending on where you melt ice sheet from. We can have the sea level change pattern deduced. And also another importance is that the GRD effects in turn feed back into ice sheet dynamics, which is important in considering, which then becomes an important factor to consider when modeling ice sheets to project ice sheet contribution to sea level in the future. So how does GRD feed back onto ice sheets? This is particularly relevant in regions where ice sheets are sitting underneath the ocean, such as Western Antarctica. And this figure is showing the effect of sea level change onto mercury the ice sheet. So the ice that is sitting underneath the ocean loses its mass across what is called the grounding line, which is this point where ice sheet starts to float into the water, into the ocean. And when ice sheet melts and the GRD, due to the GRD effects, sea level in that region falls, now there is lack of reduction in the depth of the ocean, and thus the ice flows across the grounding line reduces. And that is because ice mass across the grounding line is proportional to the depth of the ocean, which is proportional to the thickness of ice at the grounding line. So when we don't consider this regional sea level fall due to GRD effects and just let the ice retreat on a firm bedrock that does not move, and say that the ocean marine ice sheet is sitting underneath the retrograde bed slope, which means that the bed actually gets deepened towards inland. Then what happens is that the sea level ice sheet will constantly retreat over time. And this is actually showing retreat over 10,000 years. And this self-sustaining retreat is also called marine ice sheet instability. But when we incorporate this sea level fall or sea level feedback into this ice sheet model, CP model, then one sees the stabilizing effects of the GRD effects on ice sheets. And this has been proven and shown in many other model studies in the past. And this effects, or this stability mechanism, is particularly applicable to regions in the West Antarctica. And that is because in the West Antarctic region, the bedrock topography is pretty much all below sea level. And when you see the cross-section of the bedrock in West Antarctic ice sheet, you can see that the ice sheet is actually sitting on the retrograde bed slope. So we've seen that this capturing sea level feedback or GRD effects and ice sheet contributions to sea level projections is pretty important. And so this left-hand side of the plot is showing the ice sheet model intercomparison studies for the Antarctic ice sheet for the 21st century by Sorosio, and there are many ice sheet models that participated into this study. And all of these ice sheet models actually assumed the sea level change is globally uniform, or did not consider sea level at all. And so there is no GRD effects captured in any of these models. And that is not to criticize, because the GRD effects, or also called GIA, glacial isostatic adjustment effects, used to be considered as very important over long time scales, such as global centennial to decadal time, centennial to millennial time scale, or glacial cycles, and future projections will only last decades to centuries. So GRD effects are not really important, considered to be important for future projections. But now we are, I think, some of the groups are starting to incorporate that after noticing the importance of GRD effects in short-term projections as well. So what I've done is I've taken the DOE US Department of Energy's model, ice sheet model, and then incorporated GRD effects into it and applied the new, sorry about this mess, incorporated under the new ISMO 6 protocol that where the forcings extend up to 2,300. So this plot is showing sea level rise since 2015, which is the start of the simulation. And in black line is called control. It means that we're keeping the climate forcing as it is for present day. And the blue line is the low end forcing scenario in RCP 2.6. And red line is showing RCP 2.5. And purple line is showing the what is called SSP 585 8.5 scenario. And uncoupled simulation means that the ice sheet is not considering GRD effects and not coupled sea level feedback. And now the solid line is showing the results from simulation where the sea level feedback is incorporated. And you can see that there is 30%, up to 30% difference due to GRD effects in case of a really strong forcing. And so in an uncoupled simulation in the purple line, the ice sheet loses its mass by up to 2.3 meters, and now it has about 1.5 meters of ice sheet loss and contribution to sea level by the end of the 2300. So it means that another way to look at it is the time it takes for ice sheet to melt the same amount between these two simulations, and the delay in this strong forcing scenario is about 4 years, which is pretty long, still pretty long for policy time scale. And another important thing to notice is that as we go into lower and lower forcing scenarios, this delay time increases. So for example, in this very low end forcing scenario, RCP 2.6, it's going to hold the ice or stabilize the ice for about hundreds of years, if not longer. So this really tells us or gives us hope, which is that even though the sea level feedback effect is greater in the stronger climate forcing scenario, if we actually reduce the emission, then it means that we have more ice, we can save even more ice. So I think that this is pretty really hopeful message. And so here I'm showing the spatial pattern of ice corresponding to these lines. So first of all, the black line showing the control run, which means that we're keeping constant present day climate, and it also means the committed changes. And the ice thickness at 2015 looks like this. And on the right-hand side, it's showing the ice thickness changes relative to this pattern in 2015 at 21st, in the 21st century, in the 22nd, and the 23rd century. You can see that in the Western Antarctic region, the Thwaites Glacier is losing mass even in the present day condition throughout the entire simulation, which means that the ice sheet the glacier is not in equilibrium. And now showing the spatial pattern of ice thickness changes over time from the very high end forcing. And these results are showing when there's no GFD or sea level feedback. And you can see that the ice shelves in Filshirani and Ross region are completely gone, and at the same time, the Thwaites Glacier disappears by the end of the 23rd century. But when you have the GRE effects, then a lot more ice survives, especially in the Western Antarctic region, in the Thwaites region. So here is showing the difference in ice thickness changes between when we don't incorporate GRE effects and incorporate GRE effects. So red region is where we have more ice when we incorporate GRE effects. And I apologize, this has to be the other way. It's GRE effects minus no GRE effects. And this plot is also showing difference in that surface height. So in the blue-brown region is where the bad rock has uplifted due to the GRE effects. And so if we take the sea level change projected or predicted from the simulations, first of all, the final configuration of the ice thickness by the end of 2300 is that in the simulation where GRE effects are on, we can see that there is much ice coming here still. And remember that this is the very high end forcing, so the difference will be smaller, and if you look at the lower end scenario results, but the forcing is the strongest when you look at the higher end versus scenario. And the spatial pattern of sea level change looks like this. So red is where the sea level actually falls because of this uplift of the solid earth and drop in the sea surface height. And you can see that the sea level increases more as you go further away from the melting ice sheet. So I just wanted to bring back home the message of how this sea level change issue is not just about understanding physical processes, but also it really impacts human lives, especially in a very unequal and injustice way. So you can really see that no matter what, wherever we are melting ice from, wherever we are melting ice from Greenland, where we're melting ice from Antarctica. Doesn't matter where we melt ice from. These regions, um, equator regions, are going to experience sea level rise, and we are going to melt ice sheets from both polar regions, which means that these patterns are going to be closer to each other and cause stronger signals. So these most vulnerable countries are in these equatorial region and experience sea level rise higher than global mean level. But it is unjust when we look at how much we've emitted CO2 emission how much CO2 we've emitted so far per person. So the red regions here show how CO2 emissions per capita has been really big in the past up to so far compared to the other regions in the equator and further down south. And this final plot is showing the mapping of impacts of climate change, and the better you go, the more vulnerable and more impacts they get from climate change. And the main reasons why these less developed countries are more vulnerable is because they are just naturally and geographically disadvantaged at least the current configuration of the plates and continents. And they are also economically underdeveloped, so therefore they can't, they have limited capacity to manage adaptation and mitigation effectively. And so it is great that on the first day of COP28, there has been, or as of today, day 3, there has been already $600 million of lost and damaged fund established. So in summary, I've talked about how gravitational, rotational, and deformational, so-called gravity effects govern the pattern of sea level change, especially associated with ice change, and how the ice sheet change is also in turn influenced by these GRD effects. And that makes the GRD and ice sheet feedbacks an important factor to consider or capture in projecting future ice sheet contribution to sea level. And from just those detailed results, we've seen that the ice sheet contribution from Antarctica to sea level start diverging between different scenarios past 21st century. So it is really implying that what we do today really matters for today, and it'll matter for a very long time still. And yeah, so the GRD effects are most active in the Thwaites Glacial region in West Antarctica, and under the high end, forcing where global temperature rises about 4.3 degrees Celsius. The coupled simulation, which captures GRD effects, retains about 30% more ice volume compared to when GRD effects are not considered. But when we go to lower end forcings, more ice can be saved, and it's giving us some hopeful message that every step matters in limiting global emission of CO2 contributing to global warming is going to be very important. And yeah, climate change is also a justice problem, so it really goes for humanity, and that's why we're all gathered here at COP. And yes, so I think that's always an important message to remind myself. Always keep it to itself to why I'm doing science, just not just to enjoy science, but also to be useful for the community that we are doing. So thank you very much for your attention, and I hope you enjoy the rest of your talk. I guess I'm moderating myself. Is there any questions?
Yeah.
No, it's okay.
You can good to hear about the change in protocol with forcing to have much longer time horizons. I think that'd be really useful. With those, you talked about the forcings, and it seemed like you were using like different parent GCM models for different emission scenarios. Is that part of the is that part of the ISMIT protocol? And can you say something about? I guess I'm curious about the relative importance of the parent GCM choice versus the SSP. Whether you can comment on how important the choice of parent GCM is.
Right. Yeah, thanks for the question. So the rationale behind choosing those set of protocols was purely based on the availability of their lower end and the higher end forcing scenarios. So I wanted to be consistent with like which models I choose to compare the RCP scenarios, like 1.5 NOR-ESM had like 1. RCP 2.6 repeat forcing, but it also had higher end forcing available in the tier 2 experimental protocol. So I've just shown here just limited range of selections, but later on I want to include the results shown from running NOR-ESM and higher forcing so that I can compare directly between NOR-ESM 2.6 and yeah, 2.5. That was
I think that's it. I mean, I guess I'm just curious in terms of the boundary conditions in general and how, whether the spatial patterns really matter. But I guess you'll be able to answer that with those additional simulations to some extent, because then you'll be able to look at how important is the GCM choice versus the SSPs. So the UK ESM, for example, has a very high climate sensitivity, as I'm sure you know.
Yes.
So that's a pretty severe scenario.
It is. I think it was just useful to have the selections that show this dramatic, like large differences to really emphasize on the time scale of the difference. And so, because I think we kind of like gave up the community a mixed message of, oh, if you melt or if you go in higher forcing scenario, then the feedback is going to get stronger. So what does that mean? Does that mean that you're okay to melt, like go higher with the emission? And some messages got across in that manner, which is really not the narrative that we are trying to push for. So that's why I was showing these different scenarios. The UKSM is by far, yeah, and it's got really high ocean forcing as well.
Yeah.
And so, and that was an interesting choice for me, separate from this project, which is my next project, which I'm trying to still, I'm still doing it, which is when you have this GRD effects and underneath the ocean, you are also changing the solar current, and how does that then affect the ocean basal melting and the ocean forcing? So my current work is focused on that and having really high ocean forcing in UKSM was useful because, yeah, that's when I'm going to probably see the most effect in changing the bedrock elevation. Yeah.
Can I ask you one more question?
Yes.
Do you want to ask a question?
No, I'm
okay.
Okay.
Shall I ask on the mic for the people online?
Yeah. Oh, it's still on. Okay.
So the other thing was really about, so this is kind of a curiosity for me, it's not really my area, but I always wondered about GIA, so you talked about it, you touched on it. I know that physically the same kind of processes apply to GRD and GIA, but the specific question is whether, so what you said was that ISMIT did not include GRD effects. By extension, is it also true that they didn't account for any GIA rates around ice sheets? And could you comment again kind of on the relative importance of GIA? How well do we know the GIA rates around Antarctica and how do they compare to the GRD? And is it another element that should be built in or is it kind of secondary to the GRD you're talking about?
Right. So I think I didn't manage to make it clear that the GRD effects and GIA are the same. They're really the same, and using the exact same model to compute. But I think it's just the terminology, choice of terminology, like depending on who I'm communicating with. So people from the paleo community, I would refer to as GIA, and people for future from the future community, I refer to GRE because I think that's the term that's being established in the recent sea level definition paper in 2021. So, and also it is called sea level because the sea level is in GIA or paleo community, relative sea level is just the height difference between sea surface height and the solar Earth. So, yeah, GIA slash sea level slash solar Earth GRE model there. As far as I am concerned, it's exactly the same. And so now that clears up the terminology issue and going back to the ISMEP 6 not considering GRE or GIA, I think some of the models actually just incorporated GIA, well, okay, sorry, I need to also add more. I think in the ice sheet model community, GIA is only referring to deformation part, the solar Earth deformation, but it also it gets fed back by the rotational and gravitational changes. So that's where the tricky part comes from when we talk about GIA or GRD. And in the ISMEP 6 experiment, people who incorporate the solid Earth deformation, or they call GIA, it's everyone has different complexity estimating that. So some people just incorporate a less response or just a very simple depth 1D plastic model, or so it's got different complexities, and obviously you can't really say like it's completely accurate or precise, but it's just the best estimate that people can do. Yeah, and I guess one more thing to add, I've noticed from participating in the 6 new protocol this time is that it gets really complicated to calculate ice sheet contribution to sea level when one incorporates GIA or GRD, because the ice sheet model community is really used to just calculating volume above flotation to communicate ice sheet contribution to sea level. But when you start deforming or changing the sea level and deforming the solid Earth, it also changes the volume above flotation. So then it almost like becomes a philosophical question of like, what is volume above flotation? Like, do you still consider volume above flotation changes due to solid Earth deformation? Do you still consider that as ice sheet contribution to sea level? And so I think that's some ongoing discussion in the community right now. Yeah. Sorry, that was a very long answer.
That's okay. It'd be great to talk to you for,
Yes.
for a bit longer when you.
For sure, yeah.
I'm
well,
offline.
yeah. Okay. Thank you very much.